we want to take a look at another way to save for an investment that is, in essence, more approachable for a person. We're going to do a fixed monthly deposit. And in this case, we're looking at a $50 monthly deposit into an account. And the account is something that's going to earn 5.4% interest. And for ease of use, we're going to make this compounded monthly. And we're going to do this for the next 18 years. How much is going to be in the account after the 18 years? And out of that amount, how much of that is actually the interest that was earned on those $50 deposits? So to get a kind of feel of what's going on for this problem, we're going to kind of take a look at what happens after every month. Remember, the 5.4% is compounded monthly, so we don't get 5.4% that month. We get that monthly portion of 5.4% of that interest. So after 1 month, that's when we're going to make our first deposit. So we get simply $50 there. After 2 months, though, well, we deposit a new, so that's our next deposit. So we put in a new $50, so it hasn't earned any interest, but that first $50, that's going to earn some interest. And so we have the $50 plus the interest it earns, and that's 1/12 of the 5.4%. So we have 0.054 over 12 here. And so I'm going to rewrite this. This is our $50, and then I'm going to factor out a 50 from this expression. 1 plus our 0.054 over 12. So now what's going to happen is that, okay, after 2 months we have this total. So that's the new balance that we start at the 2-month time period. So after 3 months, this total balance is going to earn that portion of that 5.4% again. And then we get another $50 deposited. So after 3 months, I'm going to have the new deposit of $50. And now when I look at this, I'm going to break up this balance that was in there at the 2 months time period, because it is now earned 5.4% interest for that 1 monthly. So with that interest rate per month is at 0.054 over 12. And so I'm going to do each one of those separately. And so this first piece, that $50 is, if we look at the structure here, it's that 50 plus 50 times 0.054 over 12. Well, that ended up being just 50 times 1 plus 0.054 over 12. So I took care of the first piece. The second piece, that also is going to earn that interest rate. And so we have the original principal for that amount. And then this is going to be multiplied by that interest rate. So 1 plus 0.054 over 12, we're taking that balance, and I'm kind of running out of space here, so let me create some more space. So that should give me a little more space here. So I have, again, this piece is what was originally there, and then I'm adding the interest. So this amount times 0.054 over 12. Well, I'm just going to factor and see what this simplifies to, and we're going to see a nice pattern is going to start here. So I'm just kind of leaving these two pieces alone, and now I'm factoring out this common term, and that leaves me with 50 times 1 plus 0.054 over 12 times the placeholders. So there's a placeholder of 1, so if I expand the multiplication I get back this term. And this term has a placeholder of that 0.054 over 12. So again, look at it by expanding this product. I end up with the original expression. But now these are the same base, so I'm just going to use properties of exponents. Say, well, this is $50 plus 50 times 1 plus 0.054 over 12, plus now 50 times 1 plus 0.054 over 12, the quantity squared. And it begins to look like I have my compounding interest formula when we compound discretely here. And each one of these is a portion. So this is the deposit after month 3. That was the month 2 balance. And this is the month 1 balance. So each one of those are kind of a separate compounding interest. Here the money was just deposited, so that's t equals 0. The money was deposited a month ago, so that's t equal to 1 for compounding interest. And this money was deposited 2 months ago, and so we get t equal to 2 months, or 2 over 12 for the compounding period. So we see this compounding interest formula coming up, and so if we go, well, if I continue the pattern, I was at the end of 3 months. So let me put in that term here. The end of the 3rd month is, what if I keep doing this until I reach the last month? Well, if I continue to do this, I'm going to be at the end of 18 years, or how many months is that? Well, that's 18 times 12. And if you want to simplify that, just pull out the calculator. 18 times 12. Well, if we do 18 times 12, we get 216 months. What's the pattern going to look like? Well, we have at the very last month, the end of the 216th month, I deposit $50, and then the month before earns interest for only 1 month, and the month before that earns interest for 2 months. So I'm going to get this sequence of terms here, and it's going to end with that very first deposit that was done not 216 months ago, but 215 months ago. And so that would be 50 times 1 plus 0.054 over 12 to the 215th. So if I want to figure out how much is in the account, I'm going to have to evaluate this. And if you're good at Excel, you can figure out a way to do this with Excel to do it. But if you have some experience with algebra, you may recognize that this is a geometric series, and so the finite sum of terms of a geometric series allows us to rewrite this expression. And so this is just kind of a side note, is that if I have something of this form, I can rewrite what that sum is going to be. So I'm going to call this, the r that I'm representing here is not the same r that we're going to be dealing with, but I'm going to say is that this sum equals to some number, and so I'm trying to figure out what that number is. So we have our sum is 50 plus 50 times whatever this number is. So I'm going to kind of do a substitution to make my work a little bit easier. So I'm going to call it x, or you can call it r. So for me, x might work better than r because we had an interest rate. And so I have 50 plus 50 times x plus 50 times x squared. And I'm going to go all the way out to 50 times x to the n minus 1. How do I figure out what the sum is? Well, I can write it as a nice expression by kind of a little bit of a trick, in that I'm going to subtract, in some essence, this same sum and write out a result for it. What I'm going to subtract, though, is x times s from this. And so I'm going to write out what negative xs looks like. Well, that's negative x times each one of these terms. And so 50 times that negative x would be negative 50x. Well, 50x times that negative x would be negative 50x squared. And so if I continue the process, eventually the term before would be 50 times x to the n minus 1, and then negative x times this would be negative 50 x to the n. And now if I do this to both sides of the equation, I can now add both sides of the equation down, and on the left hand side I have s minus xs, and on the right hand side we get all these cancellations, and that's kind of the reason I lined it up that way, and I'm left with simply 50 minus 50x to the n. Well, I'm looking for what the sum equals to, and so we have s times 1 minus x equals to this 50 minus 50x to the n. Well, I'm going to factor and rewrite this as 50 times 1 minus x to the n. S is going to be 50 times 1 minus x to the n all over 1 minus x. And now I'm going to do kind of a resubstitution of what x equals to, because remember here what we're saying is x is 1 plus 0.054 over 12. And so my sum becomes 50 times 1 minus, and remember our substitution, that it's at 1 plus 0.054 over 12 to the nth power, all over 1 minus x. So 1 minus, again, 1 plus 0.054 over 12. And I'm going to do a little bit of simplification, and we're going to see how this relates to the annuity formula that you can find on the web or in a math textbook. So we have that the sum, and we're almost there, is 50 times, I'm going to do the denominator first so you can kind of see where we're going with this. Distribute the minus here, and I'm going to be left with 1 minus 1 is 0, so I have negative 0.054 over 12. And in the numerator, I'm going to leave it alone for right now. But say, I don't like having this negative in the denominator, so I'm going to bring it up to the numerator and distribute it. So our sum becomes negative 50 times 1 minus 1 plus 0.054 over 12 to the nth, all over 0.054 to the 12. And now I'm going to distribute the minus sign inside. And so if I bring the minus side inside of this parenthesis, this becomes a minus 1 and this becomes a positive. And so I'm going to rewrite it by just simply putting in the positive first. 1 plus 0.054 over 12 to the nth minus 1 all over 0.054 over 12. And so what we really did is we derived the general future value of an annuity with a fixed payment of 50, an interest rate of 5.4% annual compounded monthly. And in our case, when I was using this n here, n minus 1 equals to 215, and so n is 216. And so to finish this problem out, I can put in the value of n. It was just easier to keep track of things without putting that number in there, so hopefully that didn't cause any confusion. And that's compared to our general annuity formula. And so that general formula definition is given here, and we can kind of see that that structure is exactly the same. So now all I have to do is evaluate that sum. And so you can just pause on the calculator and see how I put it in, and we get that the value in the account is $18,194.09. Now, to figure out how much interest was paid, we just subtract off all the $50 payments. And we see that after we take out the payments, $7,394.09 is the amount of interest that was actually paid over those 18 years. If you're wondering about this part, remember there was 18 years, so after the first month we put 50 in, after the second month we put 50 in, all the way to the 18th, after the last month in that time period. That would give us 216 payments, and so 50 times 216 is at 10,800. So we see that by doing small payments over a long period of time, that we can save up to a particular amount here. And because we put money early on into an account, even though it wasn't large, the interest earned was actually able to grow kind of substantially here, in that over 7,000 of these $50 payments, total giving me 18,000. Over 7,000 was just the interest alone that was earned on those $50 payments that were made monthly.